Before we begin, make sure that you have the required notes for the day, a pencil to write with, and a scientific calculator. So that's typically the calculator that Math 8 uses. This skill that we're about to go through together is a skill that is found on the Math 8 math test. This is why you need to use a scientific calculator, because that's the one you'll be accessing for that particular state test. Your bell work in Schoology asks you to answer 2 questions and then respond to 2 questions about those 2 problems. So part A says multiply 2.34 by 10 to the 4th. So in the calculator, you should do 2.34 and then multiply it by 10 and then do the little up caret key to make an exponent and then to the 4th power. So when you do that, your result should be 234 with 2 zeros behind it, so 23,400. Part B says multiply 345 by 10 to the negative 5th power. So again, you could type that in the calculator, do 345 times 10 to the negative 5th power. When you do that, you should get 0.00345. If you type it in like that, it should be okay. If you want to put the 0 in front of the decimal, that's okay as well. So question C says, how does the original expression change in each question, and do you notice anything? So if we compare the original problem to our result, we see that the numbers out front are like the same number, but the decimal changed. So we're looking to see if there was something about the original problem that had something to do with how many times the decimal changed. Well, if you notice, this one moved 1, 2, 3, 4 to the right, and our exponent was 4, specifically a positive 4. In our second example, we don't see a decimal, but we should know that if I have a whole number, decimal is understood to be right here at the right after 345. So from this original number to the new number, it moved 3 places back, but then 2 more as well. So it went 1, 2, 3, and then it went 4, 5. Well, our exponent was a negative 5. So the exponent must have something to do with the number of times that the decimal moves. In the first example, it moved to the right, and the exponent was positive. In the second example, it moved to the left, and the exponent was negative. So the major differences between each is that while they both are what we are going to talk about today, considered scientific notation, both of them did change. The decimal did move the number of times that the exponent occurred. But specifically, if it was a positive exponent, the decimal moved to the right. If it was a negative exponent, the decimal moved to the left. So hopefully these were some observations that you made during today's bell work. So again, like I said, this topic is technically a Math 8 topic. This is a compacted course. You are going to be responsible for knowing Math 8 topics on top of the Algebra 1 topics. And some of you may already know scientific notation. If you do, great, easy lesson. If not, well, then this is your time to learn about it. So, taking a look, our essential questions. Today we're going to focus on how do you read and write numbers that are written in scientific notation, how can you compare numbers in scientific notation, and how do you perform operations with numbers expressed in scientific notation. So our first question, let's address it. How do you read and write numbers in scientific notation? Well, we need to fully understand what scientific notation even is and how it's properly written. Says, why do we use scientific notation? Well, it is a method to express very large numbers or very small numbers easily. So when we're talking about like the distance to the sun or the radius of a really small atom, things like that that are really, really big or really, really small, we use scientific notation to express them. A number is expressed in scientific notation when it is written as the decimal of a number to the power of 10. So this is very important. Scientific notation always is expressed times 10 to some power. So the base in the expression has to be times 10 to some power. Always a 10. If it's not a 10, it's not in scientific notation. the number must be greater than or equal to 1 and less than 10. So what it's really saying here is that in proper scientific notation, there can only be one digit in front of the decimal. You can have numerous digits after, to the right of the decimal, but there has to be one digit in front of it. Specifically, this cannot be a 0. So it has to be a number 1 through 9 in this spot, but only one digit is allowed in proper scientific notation. So if I have something like 23.4 times 10 to the 8th, that's wrong. There's 2 digits to the left of the decimal. There can only be one. If I have 0.234 times 10 to the 4th, well, there's something there, but it's a 0, so technically there's no digits because I need a 1 through 9, so that's also wrong. So it has to be one digit between 1 and 9 that's to the left of the decimal times 10 to some power. That would be scientific notation. Any other format, it's improperly written. So there's 2 formats of numbers when we're talking about scientific notation. There's standard form, that's just regular old numbers, and then there's scientific notation, which we just talked about. So the way that it works is if I have a number like this large number, I know that my decimal's all the way down here at the right, and I need to make it to where there's only one digit to the left of that decimal. So in order to make that happen, I would have to move this 3, 6 times. So 1, 2, 3, 4, 5, 6, and then that would be 5 to the left of the decimal. But since we moved it 6 times, it's going to be times 10 to the 6th. Now, just like when we saw with bell work, with our little investigation, it went 6 to the left, and so it is a positive exponent. If I had moved it 6 to the right, it would be a negative exponent. So for example, this one here, I still have to move it to where there's only one whole number between 1 and 9 in front of the decimal, meaning to the left of the decimal. So I would have to take this original decimal and move it 1, 2, 3, 4, 5, 6, 7 places to make it into 5.3. But since I went to the right, it's times 10 to the negative 7. Okay, same thing with these 2 examples. This one, it has to move 4 to the left, so it's times 10 to the positive 4, only one digit to the left of the decimal. And then this one, I would have to move it 3 to the right to have one digit to the left of the decimal, and so to the right is negative. So there's this little kind of, I guess, acronym that could help you. It's called LARS. Stands for left, add. So when you move the decimal to the left, you add to the exponent. It's positive. And then right, subtract. So if you were moving the decimal to the right, you're going to have a negative exponent. You're going to be subtracting from the exponent. So circle the numbers that are correctly written in scientific notation, put number X's over the numbers that are not. So first of all, anything that I see with a digit, with more than one digit to the left of the decimal, I can X it out. So there's one. Here's another one. And so those are the 2 that I see with more than one digit to the left. Now the other thing that we're going to be looking for is if our exponents are not integers. So if we have decimal or fraction exponents, that's also not okay. So I happen to notice down here there's a 1.6, that's a decimal exponent, that's not scientific notation, and then there's another one right here. So the ones that are in proper scientific notation, we've got this one, we've got this one, this one, and this one. Those are all correctly in scientific notation. So to go from standard form to scientific notation, read the number from left to right, so like a normal number. Place the decimal behind the first non-zero digit. Count how many places the decimal point should move. And then the number of moves recorded is the exponent to the power of 10, exactly like we just said. Ask how is my number in standard form small or big? So if it was a decimal less than 1, we already know we're going to have a negative exponent, and if it was originally a really big number and we're moving the decimal to the left, we're going to have a positive exponent. So our 2 examples again, this decimal is way down here. We move it 1, 2, 3, 4, 5, 6, 7 places to where there's only one digit to the left of the decimal. Since we move it to the left, it's positive. This number, I would have to move it 1, 2, 3, 4, 5, 6, 7, 8 times to get just the 5 to the left of the decimal. And so I moved it 8 times. My exponent is 8, but because I moved it to the right, it's a negative 8. Put the following numbers into scientific notation. At this time, I would probably pause the video and try to do a couple real quick and then play so you could see if you're doing it correctly. So all of these larger whole numbers, we know we're going to have positive exponents. Any of these really small decimals, when we move it, we're going to be moving the decimal to the right, and so we're going to have negative exponents. So on question number 1, decimals here, I'd have to move it 1, 2, 3 times, so 4.3 times 10 to the 1, 2, 3, so positive 3 power. If there are zeros after the decimal, you do not have to put it. So then this next one, we got 1, 2, 3, 4, 5, 6, 7 times until there's one number to the left of the decimal. So 5.7 times 10 to the positive 7th power. Number 3, we'd have to move it 1, 2, 3, 4 to get 2.6 times 10 to the negative 4th. 1, 2, 3, so 4 times 10 to the negative 3rd. This one is 1, 2 to the left, so 1.2 times 10 to the positive 2nd power. And then number 6, 1, 2, 3, 4, 5, 6 places, so 6.0 or just 6 is fine, times 10 to the, we said 1, 2, 3, 4, 5, 6, so we moved to the right, so that's a negative 6th power. So if you have something scientific notation, you're putting in a standard form, really, you're just multiplying it out and putting it back to be a normal number. If it's a positive exponent when it's in scientific notation, then you're going to be undoing what you did. So usually that was moving it to the left, so to undo it, we're moving it to the right. So don't get caught up on that so much. It's just going backwards. You're undoing it. You're multiplying it out. So you would move it to the right however many times the exponent says, and if you have blank spaces, you're going to fill them with zeros. Remember, we want to go back to a really big number. If in scientific notation it's a negative exponent, you're going to be moving it back to the left where it came from, and if you have any spaces between the decimal and a non-zero digit, you're going to have to fill it with zeros. So this was originally a really small number. So truthfully, you could just type it in the calculator like we did on bell work, literally type in the expression, hit enter, and you get standard form. Standard form is just a normal number like we've been working with forever. Whole numbers, decimals, things like that. So if I were to do 1.8 times 10 to the 5th power in my calculator and the settings are normal, it's going to give me standard form. But if I don't have a calculator and I have to sit here and do this mentally, I would know, okay, so this was a positive 5, so originally this was a really big number, and so I'm going to undo what was done. This was originally 5 places to the right. So I have 4 zeros afterwards, so 180,000. This is a negative 5, so this was originally a really small decimal. This decimal was originally 5 places back the other way. So we've got a decimal, and then we've got 1, 2, 3, 4 zeros, and then 504. So undoing positive exponents, undoing negative exponents. So, for example, this one is a negative 7, so this decimal went 7 places back to the left, so there's going to be 6 zeros, and then 68. For number 4, it's going to be 9 places back to the right to undo it, so we'd have 272, so that would take 2 place movements, and then there would be 7 zeros afterwards, so 1, 2, 3, 4, 5, 6, 7. 1.3 times 10. Now this kind of is tricky. There's an understood positive 1 here. We know that's a default exponent. So if it was a positive 1, I know this was originally 1 over here to the right, so I'm really looking at a 13. And then last one here, negative 2, means it was originally 2 back to the left, so 0.0408. Match each number with the same number written in scientific notation, circle your choice. So we're going to go really quickly, and it's really kind of like drilling, making sure it's written properly, and really just has the right exponent. So for this really big number, it's going to be a positive exponent, 1.28 times 10 to the 6th. That's how many places it's moving. I'm looking at all these exponents like they have the same number, So it's just about seeing if it should be positive or negative. That's really all that's happening. So this one would be positive, positive, negative. Now don't be fooled, that's just a negative number. This is still a large number. It's not a like really small decimal. So this would be positive, negative, positive, negative, negative, positive, negative, positive, negative. And it's all about the movement of if I would be moving the decimal to the left or the right to put it into scientific notation. So from standard form to scientific notation, already I know my decimal's down here, and it's moving 1, 2, 3, 4, 5, 6, 7, 8, 2.3 times 10 to the 8th. So this could be some extra practice for you. We're not going to sit here and do all of these. If you need some extra help with this, I will look through these and then I will post a key on Schoology for you to reference. So I have one example of going standard to scientific, and then we'll do scientific to standard. So again, to undo it, this was originally a really small number. That's why I had a negative exponent. The decimal was originally 8 places back to the left. So I've got a decimal. There's going to be 7 zeros. And then 5, 4. So the next thing we're going to look at is how can you compare numbers in scientific notation. So really like saying which one's bigger or which one's smaller, putting them from least to greatest, greatest to least, and just watching your vocabulary. Most people miss these questions because they're not paying attention to the directions. So just make sure you read the directions. So in the first example, I noticed that they're very similar. All of the expressions out in front of the base 10 are exactly the same. So I'm going to have to look at my exponents to tell me more about these expressions. And in fact, when I'm working with scientific notation, I really should reference the exponents first anyway, because they tell me more about which one's bigger than the expressions out front. So I have 6, -6, 3, and 0. We want them from least to greatest. So the smallest one is going to be 10 to the 0 power. So that's the smallest one. The next one, oh, I'm going too fast, sorry. The smallest one is -6. The next smallest is the 0. Then we've got the third is the 3. And then the largest number is the 10 to the 6th. So when we're ordering them, always look at the exponents first. And then in the event that these exponents are exactly the same, say I had a +6 and a +6, then I would have to refer to the number out front. So this time I just happened to notice they were the same, but I really never even had to look at those decimals out front. I only needed to look at the exponents on the base 10 to put them in order from least to greatest. So the next example, ascending order. So ascending is the opposite of descending. So ascending's going up. So from least to greatest. So the smallest number here, well, this is the example I was talking about. All of these are +6 exponents. That's when we have to say, okay, they're all equal to each other in terms of this. Now we need to look at the expressions out front. So since these are all the same, we're just going to rank it by these decimals. So the smallest one is 3.57, 6.73, 9.17 is the largest, so 7.63 would be the third, and then the fourth one would be 9.17. So 1, 2, 3, 4. So from the top to the bottom, 3, 1, 2, 4 is the number you should have next to them. Last two examples like this. Place the numbers in order from greatest to least, so the biggest one first. So this is all different kinds. We've got scientific and standard. So it's going to be easier to convert them all to one type. So you can put them all standard, you can put them all scientific, as long as they're in the same format to accurately compare. So I'm going to put them in scientific. So this would be 1, 2, 3, 4, 5, 6. So 3.178 times 10 to the 6th. The bottom one, 1, 2, 3, 4, 3.17 times 10 to the -4th power. So I see I have two expressions with -4 as the exponent. 3.178 is bigger than 3.17. And then these two are not the same. I have a 6 and a -5. So I'm doing greatest to least. So the largest is going to be 3.178 times 10 to the 6th. So that's the largest. The second largest is going to be the -4s, and I know that this one is larger than this one. And so the smallest one, hold on, I kind of went crazy there. The smallest one out of all of them, because the exponent is a -5, is going to be the 9.26. So we're going based on the exponent first, then the number out front. Again, putting these all in the same order. So if I were to put this in scientific notation, it'd be 2.35 times 10 to the, only moved it 1 to the right, so to the -1. And this one I would have to go 1, 2, 3, 4, 5, 6. So 6.054 times 10 to the 6th power. So this word descending is to go down, so to start from the top. So from greatest to least. So the biggest number here is obviously the +6th power. So that's the biggest number. Then these are both to the +3, so that's when we'll look at the number out front. We've got 6.223, which is bigger than that one, so that'll be the second largest, then the third largest, and then the smallest number is the exponent of -1, so it is the smallest number here. The last thing we'll talk about today is performing operations with numbers in scientific notation.